Welcome back. In this video, our learning goal is to use the electron configuration of elements to explain the trends in periodic properties. And so one of the periodic properties we will learn in this video is called atomic size. And atomic size is affected by the attractive forces between the protons in the nucleus and the electrons in the outermost energy level. So depending on an element's electron configuration, we will predict the relative atomic radius. For example, we will be able to determine that lithium is larger than neon, for example. In order to do so, we're going to have to work with something called valence electrons, because for those representative elements in groups 1 through 18 and 1 and 2 and 13 through 18, excluding the transition metals because they're a little bit harder to predict in terms of their properties. The valence electrons in those representative groups I've just highlighted are due to the number of valence electrons. And valence electrons are the number of electrons in the outermost energy level. And the group number will give you a clue to the number of valence electrons for those representative elements. So let's look at a table here that's going to help us. So for example, group 1 elements have 1 valence electron. And we can see that valence electron, we zoom in here. Let's see. This is that valence electron. 1 valence electron in its outermost highest energy level. So we know that sodium has other electrons, but the highest energy level is 3s, and it has one electron in that highest energy level. So that's the valence electron. Group 2 elements have 2 valence electrons, as you can see here. Group 3 elements have 3 valence electrons. Group 4 elements have 4 valence electrons, or group 14. So you won't see group 3A or 4A on the ACS periodic table. You'll see group 13, 14, but I just tell students highlight that last number. So 3 valence electrons for group 13, 4 valence electrons for group 14. For group 15, 5 valence electrons, 2 plus 3 is 5. For group 16, 6 valence electrons, 2 plus 4 is 6. Group 17, 7 valence electrons, 2 plus 5 is 7. And group 18, 8 valence electrons, so 2 plus 6 is 8. The only one that doesn't have 8 is actually helium, because it only has a 1s orbital, and the 1s orbital can only hold up to 2 electrons, but that's still like the outermost electrons for helium is 2 electrons there. And just to once again give you an example, one for what it means to be valence electron, carbon is 1s2, 2s2, 2p2. The highest energy level is n equals 2. So that's the reason why we're counting the electrons for the n equals 2 sublevels, 2s2, 2p2. So that's what the 2 plus 2 is for. We ignore the 1s2 because those are closer to the nucleus. They're lower energy. Those are the core electrons, if you will, there. And so valence only goes with the highest energy level. So I always look for the highest number. In this case, it's 2. And I add up the electrons in that energy level. So go ahead, pause the video, try to do the study check on your own, and then check your work with me when you're done. All right, so using the periodic table, we're going to write the group number, the period, and the valence electron configuration for the following. Let's look at calcium. So calcium is in group 2 and period 4. So it's in group 2. Period 4. And the valence electron configuration, I tend to write the full configuration. And then like I showed you in the previous example, I would erase anything that wasn't the highest energy level number. So let's just practice this calcium so you can see what I mean. So I would do 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. So what I would do is I would just write the full and say, okay, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. So the highest energy level has the highest number, so that's n equals 4. So this is the valence electrons. Everything else are kind of the innermost electrons. And so the valence electron configuration is just 4s2. And the reason why that's important to do that is that it tells you how many valence electrons. There's 2 valence electrons for calcium, and that lines up with what we just learned, that in group 2 elements, like calcium, there are 2 valence electrons. Lead, all right. So lead is, let's see here, down here. Okay, great. So this one will be a little bit more complicated because there's 82 electrons. And so when we look at this one here, it is in group 14, period 6. Okay, so group 14, period 6, let's write that down. So even just seeing that it's period 6, this is going to imply that n equals 6 is the highest energy level. So we can do the full valence electron configuration or full electron configuration, which we will, but just like we saw with period 4, n equals 4, same thing for period 6, that's going to end up being the electron configuration, valence electron configuration. But let's just go through this one just for fun. It is one of the ones that's like, you know, really down there. It's got a lot of electrons. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2, 4f14, 5d10, 6p2. So the highest energy level is n equals 6. So even if I did 4f14 and I did 5d10, the highest number is 6. So 6s2, 6p2 is the valence electron configuration, 6p2. And that's 4 valence electrons. 2 plus 2 is 4. And remember, lead's in group 14, and group 14 elements have 4 valence electrons. So we just take the highest number. So in this case, n equals 6. And then we write down the electrons in those orbitals. So 6s2, 6p2. So 2 plus 2 is 4. But don't, like I said, don't stress out too much about having to worry about f orbitals. I won't ask you something that will contain these orbitals. I know that's beyond the scope of this class, but this was a good exercise in terms of valence electron configuration because we're only concerned about whatever is located in the 6s and 6p orbitals in this case. Now coming back to valence electrons, we use something called Lewis symbols, named after the scientist who developed this method, to represent the valence electrons as dots. And they're placed on the sides of the symbol for an element. And I always start off with 1 to 4 valence electrons arranged as single dots. And I always I treat each symbol as like 4 different sides. So top, bottom, right, left, right? And so once, if you have 4 valence electrons, then you'll have a dot on each side. You spread them out, just like we learned when you were filling up orbital boxes of the same energy level, like all the 3p electrons. You half fill those boxes first. You gave each electron its own apartment, its own room, and then you started giving them roommates, right? If you had more than 3 electrons. So same thing here with Lewis symbols. Spread them out. And if you have 5 to 8 electrons, then they're arranged you start partnering them up. So the total electrons you could have are 8 electrons. And this is going to be a core chemistry skill, drawing Lewis symbols, because it's going to help you later on predict covalent compounds and how to draw their Lewis structures. And so here are the Lewis symbols for some selected elements in periods 1 to 4. And you can see, for example, all the 1 valence electrons have only 1 dot. 2 valence electrons have 2 dots. 3 dots, 4 dots, and then now 5, we start to have to partner them up. 6, you have 2 partners, and then 7, and then 8, they're all completed except for helium. Helium is stable with 2 valence electrons. It can only hold that many. So go ahead and try to do these on your own. I know the examples on the previous page, but try to do these elements, drawing their electron dot symbol, or also called a Lewis symbol. Pause the video and then come check your work with me. All right, chlorine. So first things first, you find the number of valence electrons, because remember, Lewis symbols represent the valence electrons, not the total electrons. And so for chlorine, group 17 has 7 valence electrons. You write the symbol, chlorine, and then 1, 2, 3, 4, 5, 6, 7. So notice how I kind of just went clockwise. I did the 4 electrons separated, and then I partnered them up. Carbon. Carbon has how many valence electrons? 4. Good. It says 4 valence electrons. So 1, 2, 3, 4. What about nitrogen? Nitrogen has 5 valence electrons. Excellent. So we have nitrogen, and then 1, 2, 3, 4, 5. Now, don't stress too much if you're like, wait a second, I partnered this one up, not the one on top. It doesn't matter. Just as long as you have 5 electrons, 1 is partnered up and the other 3 do not have partners. All right, so knowing the valence electrons is going to help us predict properties. So that's our goal in chemistry, is always to establish structure-property relationships. And one of the properties we will focus on in this course is atomic size, also known as the atomic radius. And that's the distance between the nucleus and the outermost electrons. So if we have an atom of carbon, then its atomic radius is the distance from its nucleus to the valence electrons. And it increases for representative elements from top to bottom of the periodic table. So what that means is that atomic radius is going to increase as we increase the principal quantum number n. So atomic radius increases going down, and then it decreases as a result of increased number of protons in the nucleus. So it decreases within a period as a result of the increased number of protons in the nucleus. So What that means is that it decreases going to the right. I know that's a confusing way to say it, but it decreases going to the right. So I always like to teach students it increases going to the left. I always point towards it increasing. And how I actually, what I tell my students is the largest, most stable element is cesium here. And if you know cesium is the largest, most stable element, then that can help you remember the trend for atomic radius. If cesium is the largest element, then that means atomic radius increases as you get closer going down towards cesium. And then if, as you go backwards or to the left, it also increases. And so that's how I remember the trend for atomic radius. Your textbook has a figure that shows, like I said, it was a little misleading to me, so I don't like to teach it that way, but it is the figure in your book, so I wanted to show it. So increase is going down, that makes sense. But then they show the arrow pointing this way, which I always think is pointing towards, it should be pointing towards increasing. But anyways, it's saying atomic radius decrease is going across. I just like to point the arrow and then just go back to the left and then say it's increasing going this way. So increases going back to the left. It is nice. I like that, showing you the relative size of each atom relative to each other. Another periodic trend is called ionization energy. And ionization energy is the energy required to remove one of the valence electrons, of the outermost electrons. And we're going to learn a lot about this in later videos. But basically, for example, sodium in its most natural form is a metal. And if we add energy, we call this ionization. So we're adding energy. We're basically trying to kick off that valence electron, because sodium has one valence electron. We're trying to kick it off. And so when that happens, we form what's called sodium cation. It's a plus charge. This is a cation. And one electron's been kicked off just out of nowhere. So basically, ionization energy is the energy required to remove one of the valence electrons. And as the distance from the nucleus to the valence electron increases, ionization decreases. So another way of saying that is that as the like, for example, if this valence electron's far away from the nucleus, then it might be easier, so it requires less energy to ionize. And so atomic radius plays a role in ionization energy. So for example, it would be, the ionization energy for cesium would be pretty low because 6s1 electron is really far from the nucleus, versus lithium's valence electron, which is in 2s1, which is in like really close to the nucleus. So let me show that in a figure here. So once again, looking at lithium versus potassium, they are all in group 1, but the valence electron for potassium is much farther from the nucleus because potassium is a bigger atom. It's lower on the periodic table compared to lithium. So that means it's easier to remove the valence electron, so lower ionization energy. So the ionization energy decreases as you go down the periodic table and increases as you go across the periodic table. Metallic character. So an element with metallic character is one that loses valence electrons easily. And we're going to learn that metals like to lose valence electrons. So metallic character is more prevalent in metals on the left side of the periodic table, these guys over here. It's less for nonmetals on the right side. And we're going to learn that they don't like to lose electrons. And decreases going down a group as electrons are farther away from the nucleus. So it decreases going down a group as electrons are farther away from the nucleus. So we can actually I think that might be a typo, so let me fix that. Because if electrons are farther from the nucleus, then it would become more metallic. So it increases going down a group as electrons are farther away from the nucleus, because metals want to lose electrons, valence electrons, easily. So it makes sense that metallic character follows the atomic radius trend. So like, for example, cesium, if you remember, that has really good metallic character. And so because it loses that valence electron easily, since it's such a big atom. And so metallic character increases as you go down and increases as you go to the left, or if you want to do it this way, and remember metallic character decreases going to the right. Basically, just remember metallic character is the same trend as the atomic radius trend. And here's a summary of the trends. So valence electrons, here we have a periodic property here. Top to bottom within a group, it remains the same. We learned that we can determine valence electrons based on group number. But from left to right across the period, they increase, you get more electrons. And then atomic radius increases going down a group, decreases going to the right, but increases going to the left. Notice how metallic character is the same as atomic radius. And ionization energy is the opposite of atomic radius. So decreases going down the group, but increases as the increase in the number of protons strengthens the attraction of the nucleus for the valence electrons. And more energy is required to remove an electron. Now, this ionization energy, all you need to remember is just the relative trends. Going right from left to right, it increases. So it's opposite of atomic radius. But if you go on to take more chemistry, you're going to learn something called effective nuclear charge. And that's going to explain kind of this concept here in a little bit more detail, but not really relevant for this class here. All right, go ahead, pause the video, try this study, check out on your own, and then check your work with me when you're done. All right, we're given the elements carbon, nitrogen, and chlorine. Which is the largest atom? So if we come back here to our periodic table, and let me just highlight them. So we had carbon and chlorine and nitrogen. All right, so atomic radius increases going back to the left and going down. Well, it looks like carbon is going to be larger, definitely than nitrogen, because it's closer. It's going, increases as we go to the left. Even though chlorine is one row down, it's still far away from, it's still quite a few spaces away from carbon. So carbon should have the higher atomic radius or larger atomic radius. Which has the highest ionization energy? So ionization energy, remember, has the opposite trend to the atomic radius. So it's definitely not carbon, because carbon had the largest atomic radius. We're looking for something with a smaller atomic radius. So now we've narrowed it down to nitrogen or chlorine. Once again, nitrogen is still a little bit farther along, closer to this side than it is than chlorine is. And so therefore, I would predict that nitrogen is a little bit larger than chlorine. So therefore, if chlorine's the smallest atom, which means its valence electrons are held like closer to the nucleus, it should have the highest ionization energy. And we can also go back to just looking at the relative atomic radius here. This is, the relative atomic radius here. So ionization energy as we see here, sorry, I should go back to ionization energy here, increases as we go to the right, slightly decreases as we go down. But I would predict that the chloride should have the highest ionization energy just based on its position on the periodic table like we just looked at there. And then which belongs to group 5A15. So looking at group 15, because this periodic table only has the numbers 1 through 18. So group 15 is nitrogen. All right, go ahead, pause the video. Let's try this again. Complete each of the following statements with decreases or increases, and then check your work with me when you're done. So going down group 16, the ionization energy should do what? Good, it should decrease. Going across period 3 from left to right, the atomic radius should also decrease. Very good. Going down group 2, the metallic character should increase. Excellent. So metallic character follows the atomic size as well. Excellent. All right, so that kind of wraps up this unit here on atoms and elements. So let's just do a bit of review on this concept map. But once again, with concept maps, you can create your own concept maps, connecting these ideas together from what you've learned in this class to other material you've learned in different classes, such as biology. But let me review over this one. And once again, definitely encourage you to create your own concept maps that help you organize all this information. So in this unit, we learned about atoms, which are made of elements. We learned how to classify those elements as metals, metalloids, and nonmetals based on their position on the periodic table. We also learned that each element has a unique chemical symbol and that the periodic table is organized by groups and periods. We also learned that atoms have subatomic particles, protons and neutrons and electrons. We can determine the number of protons by the atomic number. And the mass of the atom is composed of protons and neutrons. That's the mass number. And isotopes have the same number of protons, but different number of neutrons. And then we can determine an isotope's atomic mass by the weighted average of all its isotopes using the percent abundance and each isotope's mass number. We also learned that electrons are located in different energy levels. And specifically, not only are they located in energy levels, but they're located in different sublevels in specific orbitals. So orbitals are the probability of finding those electrons in that location. And there are S, P, D, and F orbitals. And we learned how to determine an orbital box diagram and electron configurations, which tells us the electron arrangement for that element. And we also learned about valence electrons, which are the outermost electrons. We did a valence electron configuration in this unit based on the group number, which allowed us to determine and predict certain periodic trends, such as atomic radius, ionization energy, and metallic character. All right, thank you for watching. And as always, email me with any questions.